I think you're actually recording video. Ajay, क्या questions up? I got disconnected. So we're gonna try and do just electrophilic substitution questions in this class. So starting with you can just hold on 1 second. अच्छा बस ठीक है अब सही है. अच्छा so first thing is पहले दोनों कर लेते हैं introduction to and structure of benzene ठीक है and electrophilic substitution ठीक है all both of them. So structure of benzene ठीक है. Do I have the chart open? एक सेकंड बहुत सी चीजें खुल गई हैं. So structure of benzene ठीक है. The structure of benzene is this that you have कहाँ पे अच्छा is this part the structure of benzene that you have an sp2 hybridized carbon atom and all 6 carbon atoms are sp2 hybridized and they bond together. So the question is for this reaction, so there's a benzene that's turning into a cycloalkane. So a benzene is like alternating double bonds, right? So what is happening over here is that hydrogen is getting added to it and you need a nickel catalyst for this. Okay, that is known as that thing is known as hydrogenation. ठीक है. तो और वो चार्ट भी मैं खोलूं सामने कि where's the chart. ठीक है, just a second. This one. ठीक है. So it's simply this reaction that if you have hydrogen and nickel catalyst and you've got 200 degrees centigrade, it turns into a cycloalkane. Okay, that's the first thing. And the type of reaction that's an addition reaction. Next is state the bond angles in benzene and cyclohexane, and the bond angles in benzene, that's 120 degrees. Okay, that's given over here. Okay, the structure of benzene is that every carbon is sp2 hybridized, so every angle is 120 degrees. And the explanation is going to be that it's sp2 hybridized. Whereas every bond angle in cycloalkane, it's making 4 bonds. When it's making 4 bonds, that's tetrahedral. And in a tetrahedral structure, it's 109.5 degrees. Every carbon atom is sp3. It's sp3 hybridized. So one of them is sp2 hybridized. The other one is sp3 hybridized. The next one is, we'll just stick to benzene questions for now. I said, so okay, that's optically active. Just want to stick to benzene questions. So this one, by reference to the hybridization of the carbon atom and the nitrogen atom and the orbital overlap, suggest how the sigma and pi bonds are formed in a pyridine molecule. So how are the sigma and pi bonds formed? So it's basically 6 carbon atoms. There's 1 nitrogen atom as well. And there's 1 N. And each atom is making 3 bonds. Except for the last one where it's not, except for the last one, that will not be making 3 bonds. It's going to have a p orbital available. And the p orbitals will be, the 4th orbital will be available and they would be forming pi bonds. So the first thing is by reference to the hybridization. So the first thing we're going to state is that all of them are sp2 hybridized. They have an angle of 120 degrees. So how are the sigma bonds formed? So you're going to state that the sigma bonds are formed by the sp2 hybrid orbitals. So the carbon atom has 3 sp2 hybrid orbitals, where the fourth electron is a p orbital. So remember what happens in sp2 hybridization. This is what happens in sp2 hybridization, that carbon has 3 electrons in sp2 hybrid orbitals, which are forming sigma bonds, and there's a fourth electron that's available for pi bonding, and that's your p orbital. So the fourth electron is still in its p orbital. So when carbon forms pi bonds, the pi bonds are formed by the p orbital that is available, and that is the one that's going to form the pi bonds. So you're going to state or tell that the sigma bonds between the carbon atoms or the carbon nitrogen atoms are formed when you have an sp2 overlapping with another sp2 orbital. So the sp2 orbitals will be overlapping. The hydrogen on the outside, another sigma bond is formed between the carbon and the hydrogen atoms, or between the nitrogen and the hydrogen atoms. So the bond that is going to be formed on the outside, that bond will be formed when an sp2 overlaps with an s orbital of hydrogen. Hydrogen just has an s orbital. And finally, the pi bonds. How are the pi bonds formed? The pi bonds are going to be formed when you have those pair p orbitals overlapping with each other. So by reference to the hybridization, you will state that how are the sigma and pi bonds formed in a pyridine molecule. Is this part clear, this one?
Sir, could you explain the CN bond again?
So now just a little bit in detail, right? So carbon has in its outer shell 4 electrons, like it's got electrons in the 2s1, 2px1, and 2py1, and 2pz1. So it's got 4 electrons, or it's got 4 orbitals, right? Nitrogen, remember, also has exactly the same electronic configuration. It's got 7 electrons. It's 1s2, 2s2, 2p, and 2p3. So the only difference is that one of the orbitals of nitrogen is already full. So it's got a lone pair, but it's got the same exact electronic configuration, the same number of orbitals. Now remember carbon and nitrogen both have 4 orbitals, four orbitals that have electrons in them. When carbon or nitrogen, both of them are sp2 hybridized, what happens is that both of them have this spare p orbital, both of them. Both of them. They have this spare p orbital, which is available for pi bonding. And the other 3 orbitals, they would make their normal bonds. So it's going to be, carbon would be making 1 bond over here, 1 bond over here, and 1 bond over here. So it's going to be fan shaped, right? So it will be bonded to an atom over here, an atom on this side, and it will be bonded to an atom on this side. So is this idea clear that that if carbon is sp2 hybridized, that means carbon would be making 1 pi bond. So there has to be an orbital available for pi bonding. So one of the p orbital is available for pi bonding, where the other 3 electrons are simply forming normal bonds. Yes, क्या question? Carbon subshell? नहीं, वो मैं explain करता हूँ. How would it complete its subshell? It's going to gain electron from this atom. So one of the orbital will get filled by X. There's going to be another atom that will be sharing electrons. So the other orbital will get filled by that one. There's going to be a third atom sharing electrons with it. So the third orbital would get filled by by sharing electrons. Or the fourth p orbital, that will also overlap, right? So the fourth one will also overlap, and it will overlap with some other atom's electrons. So all four of them will get fed. Naseeb, is this part clear? And so now similarly, nitrogen is exactly the same. When is nitrogen forming is sp2 hybridized? It forms an sp2 hybridized. Sp2 hybridization happens when an atom makes one pi bond. So there is one p orbital that's available for pi bonding. Okay, so that's the last one, 2pz1. And then it's got three other orbitals. So there's one orbital on this side. Okay, just 1 second. So it's got 1 second. It's not. So it's got three orbitals, right? But the thing now is that one of the orbitals over here for nitrogen is already full. One of the sp2 hybridized is already full with electrons. It doesn't need electrons, right? So that's a lone pair. So nothing will be bonded over here. It can form a bond, it can form a dative bond, but on one of the sides, nothing will be bonded because it's already full. The other ones will be bonded. There's going to be an X atom bonded over here and an X atom bonded over here. So is the difference clear that both of them have exactly the same shape? Both of them are making 3 bonds where the fourth electron is available for pi bonding. This one is also making 3 bonds, fourth electron, but the third one is not making a bond because it's already full. Okay, so that's the only difference between nitrogen and carbon, but they look exactly the same. Is this part clear? Tanya, is this clear?
Yes, sir. Thank you.
So imagine that you've got carbon atoms and you've got a nitrogen atom, and all of them are sp, because they've got a ring in the middle, right? So that means they're all forming a pi bond. So that means all of them have this pair p orbital, right? So that means they're all sp2 hybridized. So they're bonded, each one of them is bonded to 3 atoms. Except for nitrogen, because the third bond is already full. It's got a full, I mean, one of the sides is already full. One of the orbital is already full. So nitrogen will not be bonded to anything on this side. And then each one of them has a p orbital available. And those p orbitals will start to overlap above and below. And when they start to overlap, that's where the ring forms. So they'll all start overlapping with each other, and they would form a ring. So you have to explain all of this. So I think the only mistake I made over here is that the N is not bonded to H, because N is already making 2 bonds. The third one is already full. I mean, the third one is already full, so it's not going to be, it can be bonded to an H, but not at the moment. So you just had to tell that it's sp2 hybridized, and the sigma bonds between carbon-carbon, that's sp2 overlapping with sp2. So it's all sp2 overlapping. The carbon and H bond, that's an S overlapping with an sp2. The pi bond or the ring or the pi electron cloud, that's a p orbital overlapping with a p orbital. That's all you had to tell. Is this clear, this one?
Yes. Yes, sir.
Okay. Now the next one, just a second. Okay, some other question related to the structure of benzene. So okay, let's move to electrophilic substitution for now. Remember electrophilic substitution, that's this part. I'd say most of the questions are kind of mixed up. So, I mean, the question will be kind of related to other parts of organic chemistry as well. So you've got to, this is an AS question. You've got this thing and you have to turn it into this thing. So you've got a ketone and you have to turn it into an alkene. So let me just open, where's AS? I think this is an AS chart. So I've got a ketone, and I want to turn it into an alkene. So how do I turn it into an alkene? I will first reduce it. So if I reduce a ketone, it will turn into an alcohol. And then I can dehydrate that alcohol and it will turn into an alkene. So this is the path that is probably going to be followed in this case. So this molecule over here, so the double bond O will turn into an OH, and so it will turn into an alcohol, and then that alcohol will be dehydrated. So this is LiLH4 or NaBH4 as well. That's your reducing agent. And then the alcohol getting dehydrated, so the OH will go away, and in its place, the H will be lost from the neighboring carbon atom, and it will turn into an alkene. That's Al2O3 plus heat, or concentrated H2SO4 plus heat. As a next one, reduce the identity of compound H. We did that. Suggest reagents and conditions for each step. Step 1 as well. So the step 1 is electrophilic substitution. You got a benzene, and you got this thing getting attached to it. So what is this reaction? So that's electrophilic substitution. So if I look at the notes in electrophilic substitution, right at the end, there's a thing called right after 3, 2, 4, 6, and 3, 5. There's a thing called alkylation and acylation. Now, alkylation is that benzene has a lot of electrons. It's got an electron cloud. If you have a halogenoalkane, if you've got a Cl somewhere, the carbon has a partial positive charge, and that partial positive carbon is going to be attracted to the electron cloud. So the carbon chain will get attached to benzene. It will get attached to one of the carbon atoms. And the Cl gets knocked out. It will eventually form HCl. And the same thing happens with acylation as well, that if you have an acyl chloride, which is that if you have a serial bond O and Cl, you got a carbon chain and you got a serial bond O, the benzene will be very attracted to the serial bond O with the carbon over there. The Cl will get knocked out and the carbon will go and join with this thing, and HCl is going to be the byproduct. So this is this thing happening. This is acylation. You need an AlCl3 catalyst for this. So this reaction over here, so let me go back and disconnect this thing with this thing. So my reagent would be, this carbon over here will be an acyl chloride. It will be C double bond O and Cl. This carbon is basically a CH3.
From what exam is this?
Which one?
Which exam is this question from?
No, this is a compilation. I'll share the workbook for you. This is not a specific exam.
So what is the difference between alkylation and acylation? Like they both knocked out Cl.
Yeah, they're both kind of exactly the same. It's except that over there that you've got a simple carbon chain getting attached to just a halogenoalkane, right? So the carbon is positive. Over here, you don't have a simple carbon. You've got a carbonyl serial bond O and then a Cl. So the carbon is positive. Same thing happens, except that it results usually in the formation of a ketone. Is that clear?
Yes, sir.
So that's alkylation, and the reason for that is you need an AlCl3 catalyst, and the reagent would be this thing. It's called ethanoyl chloride. It's 2 carbon atoms, and it's going to be called ethanoyl chloride. Is that clear?
Yes.
So then you have the next one. We've done with this one. This is also, now he's saying that benzene reacts with SO3 and this is produced, which is SO3H, right? Now, SO3, this reaction is not in your course, but the reaction that is in your course, that's electrophilic substitution, and I'll share the mechanism with you. So it's this one. What happens is that you've got a benzene and it's got this electron cloud where all the p orbitals are overlapping. So if you have an electrophile like NO2 plus 1, what happens is that the NO2 plus 1 electrophile is going to be very strongly attracted to one of the unreacted p electrons, right? And the NO2 is going to bond with it. So your carbon electron cloud will become partial. And in the next step, the H will lose its electrons and the carbon electron cloud will be complete again. And so that's substitution. So the H goes away and the NO2 takes its place. So it's a very standard reaction. And it's going to be, I mean, benzene mostly has electrophilic substitution. So that is going to be asked very, very often. So over here, in our course, we have a reaction called nitration, that's NO2 plus 1, but over here is given us SO3H plus 1. So I'm pretty much going to do the exact same thing, which is that the SO3 is going to be attracted to the electrons in benzene. The SO3 is going to bond with one of the carbons. And the benzene electron cloud will become partial. So instead of having a complete electron cloud, the electron cloud will go missing at this point. And then in the next step, I don't think that they're just asking for the intermediate, but the next step is going to be that the H will give its electrons back. And the HSO4 minus 1, which was formed earlier, is going to be attracted to the H. So this is exactly what happened in over here as well, that when the H lost its electron, where did the H plus 1 go? It got attracted to the electrons in the HSO4 minus 1 molecule. So that is exactly what's happening. Okay, so write an equation to show how the H2SO4 catalyst is formed. So you're saying write an equation to show how the H2SO4 catalyst is reformed. So that's happening over here. That the HSO4 minus 1 grabbed the H plus 1 that was lost and it ended up as H2SO4 back again. Is that clear?
Yes, sir.
Yes.
So then the next one is now you're saying suggest reagents and conditions and name the mechanism for this reaction. So now what's happening is you've got an alkyl chain getting attached to benzene. That's again what we just did. That's alkylation. Okay, we did this. That if a carbon chain gets attached to, where is it? I mean, it's over here. We just did this. That if you want a carbon chain to get attached to a benzene, the carbon must have a Cl attached to it, because then it's going to have a slight positive charge. So if I go back over here, this thing C12H25, it must have a Cl attached to it, because that Cl will result in one of the carbons to be positive, and that positive carbon will get attached to the benzene. Is this clear, this thing?
Yeah, shouldn't you mention about the catalyst? Okay, never mind.
Yeah, that's the AlCl3 catalyst, and the mechanism is going to be called electrophilic substitution. So then the next one is that's the next one. Benzene reacts with bromine in the presence of aluminum bromide catalyst to form bromobenzene. This is a substitution reaction. No addition reaction takes place. Explain why no addition reaction takes place in benzene. Addition does not take place because the benzene electron cloud is or benzene structure is benzene electron cloud is stabilized when p orbitals overlap. The explanation for this is that since we are talking about benzene, why does no addition reaction going to take place over here in benzene? The answer to that is that the p orbitals are very distributed. When you have a benzene structure, the p orbitals are very distributed and they have a very low charge density, which basically means that they're not going to be very reactive. So they're not going to be very reactive. And that also means that if you have, like over here, where's the carbon? So in the middle, if it gets a positive charge, even that positive charge has a very low charge density. So it doesn't really attract other things. Now compare this with alkenes. The problem with alkenes is, like if I go back, if I go and have a look at alkenes and electrophilic addition of, just 1 second. Where's alkenes? So if I have a look at alkenes, why do their p orbitals go away? The reason the p orbitals go away is that when bromine takes the electron away, the carbon gets a very strong partial positive charge. So this carbon over here, searches for the negative ion and attaches itself. It's got a very strong positive charge. The problem with benzene is that when somebody takes electrons away from it, the benzene does get a positive charge. So if you go back to benzene, keep this thing in mind that when you have an alkene, if bromine, one of the bromines positive takes away the pi electrons and bonds with the carbon gets a very strong positive charge, which is why it grabs onto the Br-1. But that is not the case in benzene. Because if you look at the structure of benzene and electrophilic substitution, same thing kind of similar happens when the bromine grabs one of the p orbitals and bonds with it. The positive charge is very, very small. It's got a very, very low charge density. Why? Because there's so many electrons that the positive charge is kind of almost negligible. There's hardly any positive charge on this. So, which is why it's not able to actually pull any other thing and get attached to it. So the only possible way is that the electrons kind of distribute themselves, and these electrons also become part of this, and the H eventually leaves. So this is what happens. So this one is a lot more stable structure, even due to the delocalized electron clouds. Is that clear that the positive charge is not going to be very big, which is why it's incapable of attracting the Br-1 that had broken away. So the Br-1 does not get attracted to the positive charge over here, unlike in an alkene. Is this idea clear, this thing?
Yes.
Okay, so the Br-1 does not get attracted to the positive charge over here. It instead gets attracted to the H over here. And the electrons over here, they kind of get mixed up with this pi electron, and the H leaves, and then that goes in bonds with Br. So the idea is that the ring system is a very, very stable system, and it's very hard to actually get rid of it. So benzene electron cloud is stabilized when p orbitals overlap. And draw the mechanism, so it's the same mechanism, Br+1. So he's saying there's a Br+1 electrophile coming in, so it's exactly the same mechanism. So you got a benzene, you'll be frequently asked to draw the same mechanism. So Br+1 comes in, grabs one of the electrons from the pi bond, pi electron cloud, and your benzene electron cloud will become incomplete. And in the next step, the H is the one that's going to lose electrons. And the H will lose electrons and it will leave. Then he says, write an equation to show how the AlBr3 catalyst is reformed. So what happened over here is that it would become AlBr4-1. And that AlBr4-1, the Br is going to get attracted to the H. So the H that is lost will get attracted to the AlBr4-1. It's going to take the Br back and form HBr, and an AlBr3 catalyst is reformed. Okay, so we are talking about the last part, which is this one. like over here we had FeBr3, but how is the catalyst reformed? Because the H is lost and that grabs the PR and the FeBr3 is reformed. As the next one, suggests why bromination of phenol occurs more readily than the bromination of benzene. So what happens in this case? Now this is just electrophilic substitution. Now there's certain types of electrophilic substitutions where the reaction is a lot faster. So you've got two types of electrophilic substitutions. There's a 2,4,6 directing effect. So when benzene is bonded to, just a second. So when benzene is bonded to an electron donating group, what happens in that case is that you've got a strong electron donating effect, and the charge density on positions 2, 6 and all the other electrons, they get repelled and they accumulate on the other side. So the electron cloud is not evenly distributed. So what happens in this case is, if you have an electron donating group, the electron density becomes greater on that side. And all the other electrons, they get repelled and they accumulate on the other side. So on positions 2, 4, and 6, if this is your reference, if this is position number 1, then 2, 3, 4, 5, and 6. So on positions 2, 4, and 6, the electron density is significantly higher, which is why electrophiles, if they are going to get attracted to benzene, they're going to be attracted to these positions, either 2, 4, or 6. 2 and 6 are considered to be the same position. So you often see this as just 2, 4. So the electrophiles are going to be more strongly attracted to these positions. So if I do bromination, the same reaction for methyl benzene, the bromine is more likely to be attached to position number 2 or position number 4 instead of 3 and 5. Same thing with chlorination, same thing with nitration, that the NO2 will prefer positions 2, 4, and 6. Now he's talking about phenols. Now so who's 2, 4? Who's the electron donating group? You've got phenols, you've got alkyl chains, you've got amides, you've got amines, and you've got chlorine as well. So he's talking about phenol. Now the thing with phenol is, like if you have a look at phenol has a very large electron donating effect. It's got a very, very strong electron donating effect. Because oxygen has lone pairs, and these lone pairs, they overlap with benzene's pi electron cloud. So the electron density is significantly higher at position number 2, 4, and 6, which is why the reactions, electrophilic substitution reactions for phenols are significantly faster. So if I have a phenol and if I do bromination, bromine will get attached to all 3 positions. You don't even need a catalyst in this case. Chlorination, no catalyst is needed. The reaction is significantly faster. Nitration, again, no H2SO4 needed. You can even do this with dilute nitric acid, and the NO2 will get attached to positions 2, 4. And if you do concentrated nitric acid, it will get attached to all 3 positions. So the question was basically, why does phenol have a faster reaction? So this is the statement that you're going to write, that the lone pair on oxygen in hydroxy group, and that applies to NH2 as well, it overlaps with benzene's pi electron cloud and significantly increasing the pi electron cloud density, which is why electrophiles will be strongly attracted to benzene, and you'll have a faster reaction and you'll have much milder conditions. No catalyst will be needed for this. So is this answer clear for this one?
Yes.
Okay, so 2 marks for that. Now you're seeing there are 4 different carbocations with the formula C4H9 plus 1. So you just have to draw the 4 structures, I guess. So one of them could be that the middle one could be a carbocation, right? So there's going to be 3 H's with this one, 2 H's, 3 H's, and 1 H with this one as well. Or you could have this one could be a carbocation, and this could be 3 H's, 3 H's. That's also C4H9. Or you could have this one as the positive one. So there's going to be 1 H with this, 1 H, and 3 H's. So these are your 4 carbocations. Can you tell me which of these carbocations is the most stable one? Which one has the lowest charge density?
Structure
Third
three.
one.
कौन सा? The third one, right?
Third one.
Okay, so the third one is going to have the lowest charge density because ticket number 3. And the reason for that is that you got electron donating groups. Lots of, if you have more carbon chains, they're going to donate electrons and this positive charge is going to become very small. You're going to have a very small positive charge, which is why this is going to be the most stable one. The least stable one is probably going to be, I mean, this is the 2-degree carbocation. This is your 1-degree carbocation, and this one is also 1-degree carbocations. 1-degree carbocations are the ones that have 1 carbon chain. They're the least stable. As I play this one, this compound K, and that's your starting material for the synthesis of gallic acid. A student suggested the first 2 steps of the synthesis for this reaction. Now, so first one, construct an equation for the formation of NO2 plus 1 ion. So again, that's given in the notes that how are NO2 plus 1 formed? Where is nitration? Nitration is a 2-step reaction in which the first step is that you produce NO2 plus 1. So you have to remember this equation, it's nitric acid plus sulfuric acid, and it ends up forming the NO2 plus 1 electrophile. And then that electrophile goes and binds to the benzene. So construct the equation. So we can do that H2SO4, 2H2SO4 plus HNO3, and it's going to form NO2 plus 1. And H3O plus 1. And again, he's talking about the NO2 plus 1. So where will the NO2 plus 1 get attached? The N has an electron donating effect. So the electron density is going to be significantly higher at these positions, 2, 4, and 6. We already have something attached at 4. So the NO2 plus 1 will, so the NO2 plus 1 will get attached to the benzene on this side. And the intermediate is going to be that I mean, the NH2 is still there. The NO2 will get attached to one of the carbons in benzene. The electron cloud will become partial on this side. There's going to be an H over there as well. And in the next step, the H is the one that's going to lose electrons. State the name, that's electrophilic substitution. Okay. We'll continue tomorrow. I'll share a schedule with you. We'll continue tomorrow. We'll just do more electrophilic substitution questions, and we'll do other organic questions as well. Okay.
Sir, can you share this and the spider web for the AS reactions?
I'll share all of them right now.
Okay. And sir, did we start the NMR and carbon 13 thing?
No, we haven't started. We'll do that.
Okay, thank you.
Sir, I need access.
Can you share me screenshots? Share the screenshots with me.
Sir, I'll do it in DM, okay?
Okay. Okay. हसीब A2 crash course है मेरे ख्याल से ढूंढनी पड़ेगी. There is an A2 crash course. ठीक है.